Hey guys, this video is going to be covering heat and temperature and focusing on their relationship. And I'm going to try to make this as quick and painless as possible, but as thorough as possible. So please just rewind and watch the parts that you need to. Hopefully it won't be as arduous as the ideal gas law video. The three main questions here is what is heat, what is temperature, and then are these terms interchangeable? A very quick answer to the last one, which is what a lot of people want to know. Are these terms interchangeable? Absolutely not. So let's go ahead and just write right now, no, they are not interchangeable terms. However, they are related. So very quickly, just to kind of get this all out in the open, heat is a form of energy. All right, this is just a form of energy. Now, I get a lot of people asking questions that, well, is heat a measure of hotness or coldness? And it's not, actually. That's a dangerous path to go down. There is a relationship between that, but you just have to think of heat as energy. All right, so in general. And this is something that we would measure in joules. Units are oftentimes neglected when somebody's trying to learn something for the first time, and I actually think it's very easy. It's much easier to use the units. So heat and energy are interchangeable terms, and heat is oftentimes a kind of transferable energy. So I'm going to just write here that you can transfer heat. So you can pass heat from one place to another. And this video is not going to look at heat transfer very much. There will be a separate one for that. But this is just a very important thing to get in your mind, that heat is the energy. And if here we're talking about a gas, that can be described in many different ways. The gas molecules are moving, but they're moving in three different sorts of ways. One of the ways that they're moving is translational. I'm going to just write that as a T. The other way that they're moving is rotational. So some of them are spinning. And then they're also vibrational energy. They're vibrating back and forth. What we are primarily going to focus on here is the translational energy. This just means moving from one location to another in the chamber. So vibrational, the one on the right, would be just shaking in place. So you can think of something that's sort of vibrating, wobbling. It's not moving from point A to B, but it is moving. We are not going to consider that kind of energy. The R, the rotational energy, would be the spinning of the molecules in some way. We're also not going to really focus on that. So we're just going to look at the translational energy as a marker for the energy of the system. And the energy of the system, then, we can use the idea of heat to explain how that energy is present and how it can be moved. All right. So next up, let's look at, let's see, what shall we look at? The temperature, the definition for temperature. So I'm going to kind of shift this up. So we have heat up here. Now let's look at temperature. Temperature is actually going to be a measurement of the average. Okay, so this temperature is a measure of the average kinetic energy of the molecules or the particles of the gas. Now what's very important here is temperature. Okay, we're going to measure, I'm just going to use Kelvin for now. You can use degrees Celsius, not really degrees Fahrenheit. It's complicated, that scale system, but let's just use Kelvin for now. It's not degrees Kelvin, just Kelvin. And this temperature is going to be a measure of the amount of kinetic energy that's present. It isn't the kinetic energy, but it's a measure of it. So temperature describes hot and cold, if you will, or high kinetic energy and low kinetic energy. If we did a conceptual test and we touched hot things and cold things and also knew how fast the molecules were moving in each, we would see that for hot things, the molecules are moving much faster, and for cold things, the molecules are not. A really cool experiment that you can do with this is if you take hot water and you take a bath of cold water and you try to dissolve a substance in it. The substance will dissolve a lot quicker in the hot water maybe like food coloring or something, it will disperse a lot faster because the molecules are moving and spreading out the little dye molecules throughout the system. So it's an example of, you can kind of see temperature is a measurement of the kinetic energy. It isn't the kinetic energy itself. And so that's the biggest difference. So just to summarize that really quickly, heat is energy. Temperature is a measurement of energy, or it's a marker that represents how much energy is present. So that's very important. In the next half of this video, we're pretty much halfway done, is we're actually going to break into that mathematically and see what happens. Okay, so then how are temperature and heat related? Okay, so if you add more heat to a system, at a certain point, the temperature will rise. If you remove heat from a system, at a certain point, the temperature will lower. But you can add heat to a system and not increase the temperature, because all you're doing by adding heat is adding energy to the system. And if you don't add a substantial amount of energy, enough to raise the average kinetic energy of the particles, then you're not going to register a temperature difference. And so there's a lot of other energy that's going on there that we're ignoring for right now. We're just focusing on the kinetic energy. So we are going to see, how do temperature and heat relate? They are directly related. As a side note here, we're going to call the letter Q the variable for heat. This is conventional to use. And we're going to say that Q is somehow proportional to temperature, but they're not the same thing. Okay, it's just like pressure is proportional to temperature, but they're not the same thing, right? So that's very important. So let's take a look at our next slide and see kind of how we can actually start to crack this idea. Okay, so the answer to any question of relationship between variables is found through experimentation and data analysis. Now, you can also find relationships theoretically, but that's another kind of ball game. Now, throughout the class so far, we've done a lot of experimentation, actually a ton of experimentation. Almost 80% of the time we have spent collecting data and looking at relationships in our board meetings. And so what we're going to do is the same thing here. We're going to use the simulation from the wonderful people at Phet, and we are going to take a look at how heat and temperature are related, or really how is energy related to temperature. So let me add a picture here real quick. Okay, so here I have a screenshot of the experiment that I was running, and this is the wonderful Phet Colorado University, or University of Colorado, I think at Boulder. Thank you to them. Donate money to them if you can. This is a cool simulator, and what I've done is here I've held the volume constant so that as the temperature, as the molecules start to move faster, they're going to be pushing on the walls. So here I have this heat control, and I'm going to add heat. Okay, so I'm going to add a little bit of energy here, and what this is going to do is it starts making the molecules move faster, which makes sense because if they are given more energy, and remember our marker for energy is kinetic energy, and I look at this little measurement tool here that shows me the average speed of the molecules, 427.74 meters per second, super fast, and I get this reading of temperature over here. Okay, and then I record that. So I say, when the speed of the molecules is 427.74, what is the temperature? Now, why the heck am I measuring speed? Instead, I was telling you that we're trying to relate energy to temperature. Well, kinetic energy is made up primarily of velocity, right? The mass of the particles does matter too, but the velocity of the particles is a big portion of it. So I'm going to track velocity and temperature, and I'm going to try to take a look and see if there is actually a correlation between those, and if so, there's probably a correlation then between kinetic energy and temperature. So let's pull up a second picture here. All right, try to get this out of the way. So here is, you can see I've added more heat, and in this frame you can see the speed of the molecules is greater, and the temperature is also much greater. And so on the next slide I'm going to show you some of the actual data that I collected in graph form. Okay, so here we have some data which is temperature versus velocity. Now I've done a bad thing and I have not written axis labels. So this is temperature in Kelvin, and this is velocity in meters per second squared, or average velocity. And what I did, I collected there, you can see about 5 different data points. You could probably do more, but 5 is looking pretty good here. And I tried out some different best fit options, and the quadratic fit came out the best. So I have this equation that we have right here, y equals 0.000018 x squared, and I'm going to leave off the other stuff for now. Okay, so we look at this and we say, okay, if this is really the best relationship, then most likely linearizing this graph will indicate that temperature and velocity have a really nice, temperature and velocity squared have a very, very nice linear fit. So let's see if that's actually what happens. So I'm going to move this up and away here, and let's add the linearized graph. Okay, awesome. So here is the linearized graph. Once again, for this graph, we have t versus v squared. If you're struggling on how you are supposed to linearize something, see me and I can try to get you some information to help. So this generic function is y equals mx plus y initial or plus b. You can write either one. Okay, we're going to say that this is 0. Let's make it 0 just to simplify the situation. Now I'm going to replace the variables with the variables of my graph. So y is temperature. M is some number that I'm going to try to figure out some information about. And x is velocity squared. So at this point, what would be interesting to see is if I graphed temperature versus kinetic energy, do you think I would get a linear shape? So think about that, pause the video, and try to think. If I graph temperature versus kinetic energy, would I get the same shape as this graph? Yep, you most certainly would, because if you think about it, if this was kinetic energy down here on the x-axis, all we would have here are multiplying this by a constant here, so we'd have t versus k, which is 1/2 mv squared. And so that's kind of cool. So I'm going to try to write the equation again. T equals some value, some slope, m, times kinetic energy, okay? And let's go on to a new slide so we have some space to play around with this cool idea. So we have that if y equals mx plus b, as we saw, because that is the shape of our graph, y was t, m is our slope value, and x we're going to make k now instead of v squared. But if I expand k to be 1/2 mv squared, so I have t equals some value of slope times 1/2 m v squared, I get back now to my original graph form, and I'm going to make a parentheses here and here, because what I'm going to say is if from my function that I got in the data was this, perhaps the m over here is all this. So inside the m, the slope, there is some information about the mass. Somehow we're going to figure out the mass of these particles, maybe molar mass, maybe something else. And there's a 1/2 in there, and we want to figure out what the rest of this is that's in the m. And so far we see there is a direct correlation between the temperature of the gas and the kinetic energy of the gas. So the amount of kinetic energy, average kinetic energy of the particles, is basically represented by the temperature. And so let's try to see if we can figure out what else is in the slope. Okay, so just to clarify here, this m is a number, right? I'm going to make it a hash mark here because it's a number, and the m that's boxed over here on the right, that is mass. So what I'm going to do is I'm going to figure out what the molecular mass of my gas is by knowing what kind of gas I put in, and I'm going to divide the slope by that number. So that would get rid of this. And so now I have this t equals some number times v squared. And this some number value, so let's kind of scoot this up a little bit. This some number value, remember when we talked about like different tools to analyzing graphs and figuring what the slope might mean, we always divided or multiplied by a constant to see what we could get that might be useful. So if you divide by a constant, you multiply by a constant, play around with different things, the two constants that have been coming up a whole lot here are R and the Boltzmann constant. R always related somehow to molar mass, and the Boltzmann constant always related to the molecular mass. So if I divided my slope by the molecular mass, what I found was, the molecular mass was gone, and then I first divided by the Boltzmann constant, and nothing really showed up very easily, and then I multiplied by the Boltzmann constant. And when I multiplied by the Boltzmann constant, what ended up happening was, so I took my slope, so let's make this slope, and I took that, it's a number, and I multiplied it by the Boltzmann constant, because I'm just trying to see what else might be included in here. Now remember, I've also divided my slope by the molar mass. That's why I picked the Boltzmann constant. And what I'm left with, which is really strange, is this fraction, 1/3. So this indicates that somehow in the slope, there's a 1/3 in there, there's the mass in there, and there's the Boltzmann constant. So let's backtrace and see if we can put it back together. Temperature is equal to this hashtag, this number, which the mass was divided out, so there's a mass in there. The Boltzmann constant was multiplied through, so there's a Boltzmann constant down there in the denominator, and I was left with 1/3, so I'm left with this, and don't forget what is my independent variable, v squared. So I'm left with this really interesting little thing here. Okay, this statement, T is equal to m over 3 kb times v squared. Now, that whole discussion may have been really confusing to you, so just reverse the video and watch it again and try to see if you can just keep track of what we're talking about here. We are bouncing around a little bit. Okay, so we're ready to take this home. Okay, so we've got this value here, and I'm gonna write it down, and then we're gonna flip to a new slide, and we're gonna see if we can put this back together and to make something that's meaningful and useful. Okay, let's do it. 2 minutes. Okay, let's do this. So we've got T equals m over 3 kb v squared. Now I want to put this back in terms of kinetic energy, so I'm going to multiply both sides by 1/2, because I know if I have a 1/2 on the right side, then I can make kinetic energy. So I've got 1/2 times T is equal to, okay, I'm going to do 1/3 kb, and pull that out on the side, times the 1/2 times m times v squared. So you take a look at that for a sec, pause the video if you need to see. I just stretched out the numbers, kind of rearranged them slightly. Okay, so now I've got 1/2 T is equal to, okay, 1/3 times the Boltzmann constant times kinetic energy. Alright, we're kind of getting sort of somewhere. Let's try to get rid of these denominators. So I'm going to multiply by 3 kb on both sides. Yeah, that will work. So I'm going to have 3/2 kb times T equals kinetic energy. Yeah, that works. So this gets rid of some of the denominators, and I have this relationship. Well, guess what? This relationship, kinetic energy, I'm going to make it Ke just so not getting confused with the Boltzmann constant. Kinetic energy equals 3/2 Boltzmann constant times temperature. This is one of the equations that's on the equation sheet for the AP2 exam. A very famous relationship. Now there are other ways to theoretically derive it. Very quick 10-second or 15-second review of what we just talked about. Heat and temperature are not the same thing, but they are related. We're going to look at heat as a transferable form of energy. When we add heat to a system, we notice that the kinetic energy of the molecules increases. When the kinetic energy of the molecules increases, we register that as a higher temperature. Now, how our heat, or kinetic energy in this case, is our marker for energy, how is that related to temperature? Well, you can see right here. Temperature is multiplied by 3/2 times the Boltzmann constant, and I have kinetic energy. So this is how we can convert joules almost into Kelvin, or Kelvin into joules, by this sort of relationship. So I encourage you to watch this again to make sure you didn't miss any parts of it. But the major thing that we got from this video is this equation and the idea conceptually that heat and temperature are not the same thing, but they're related in this way or in some way like this.